Okay, we go on the second part, interstitial in the point defects. Okay, so what is the interstitial? Okay, it occur when an atom in a crystal can occupy an interstitial site between the surrounding atom in normal atom size. Okay, in metal, a self interstitial introduce large distortion. Yes, that's the effects. Okay, in the surrounding lattice because the atom is substantially larger. Okay, larger than the interstitial position in which it is situated. Okay, this defect is not highly probable and it exists in very small concentration, significant lower than for vacancies. Okay, you can see from this diagram that the same atom, they are not in the right plane, okay, the right column, because they will distort of our plane. Okay, so you have to remember what is the interstitial defects. Okay, we can see here they have a two type of the point defects. The first one is a self-interstitial and the second one is a vacancy. Okay? If you have to draw the diagram, as an example, you have to draw something like this. Okay, how about the point defect in iron crystal? Okay, you have to compare it with the solid crystal and the ionic crystal. You can see that the ionic is a stem of an atom, but ionic is a transfer to another and another because they have a positive and negative ion. Okay, in the ionic crystals, point defects are more complex. Okay, due to necessity to the maintain electric neutrality. Okay, that means that they have to positive to negative one. Okay, the point defects that occur in the ionic crystal are known as Scotty imperfection and Frankel imperfection. Okay, there are two, Scotty and Frankel. Okay, for in the ionic crystal imperfection, okay, or defects. Okay, the first one is by the Scotty. Okay, the Scotty. Okay, that means that occur when two opposite charge ions are missing. Okay, are missing. Two opposite charge ions are missing for the Scotty. Okay, this one for diagram. From an ionic crystal to create a cation anion divergency. Okay, that means that you are missing of the positive and negative ion. Okay, how about the Frankel imperfection? Okay, occur when positive cation move into a interstitial site in an ionic crystal. Cation vacancy is created in normal ion site. That means that the positive cation move into an interstitial site. So it moves to this one. This one is the original one. Okay, they move to the interstitial. Okay, with the ion. Okay, so you have to differentiate between the Scotty and Frankel. Okay, if the you have to draw the diagram as this one. Okay, you have to make a very clear comparison between the Scotty and Frankel. Okay, and then the next is about the impurities. Okay, in the point defects. The first one is a vacancy, second one is interstitial, and the third one is a impurities. Okay, we know that a pure atom consisting of only one type of atom, that the pure one. Okay, just is not possible. Okay, we know that it's not possible except we control the environment, control it with the sample or materials. Okay, impurity or foreign atom will always present in the normal temperature or normal condition. Okay, and some will exist as crystalline point defects. Okay, most metal are alloy. Okay, which impurity atom have been added intentionally to impact specific characteristic to the material that I will discuss before, that the addition or add up of the material give more properties, increase their properties in terms of hardness or something else. And then alloying is used in metal to improve. Okay, remember that. Alloying is used to improve the mechanical strength and corrosion resistance. Okay, the addition of impurity atom to a metal will result in the formation of solid solution. Okay, solution. What is the definition of solution? Okay, when solute atoms are added to the host material, the crystal structure is maintained and no new structure are formed. Okay, impurity point defects, okay, are found in solid solution. Okay, which there are two types. Okay, the first one is a interstitial and substitutional. Okay, that's mean that interstitial is a small one. Okay, substitutional is a bigger one. Okay, there's a differences between interstitial dengan substitutional. Okay, and impurity is the substitution of a regular lattice atom with an atom does not normally occupy that sites. Okay, the atom may come from within the crystal. Example is chlorine atom on a sodium site and ACl crystal, or from the addition of impurities. Okay, so there has a example here in terms of chlorine and ACl. Okay, and ACl. Okay. Okay, for the initial defects, okay, what happen if the initial defect, okay, form when extra atom or ion is inserted. The keyword is inserted. Okay, substitution to do when one atom or one ion is replaced by different type of atom, the another material or the other atom. Okay. So what is it? They have a two outcome if impurity B added to the host A. Host A does mean that is a original atom. Okay, impurity is a B is added. Okay, the first one, solid solution of B in A. Okay, random distribution of point defects, crystal structure maintained. Okay. So example here, they have a two type in term of substitutional and interstitial. Okay, the first one substitutional alloy with the added with the other material. Okay, they have a law actually, the size not more than 50%. At least the maximum is 50% from the original one, from the host one. Okay. And then the second one is about the interstitial alloy. Example is a carbon in ferrum. We know that the carbon is very small atom. Okay, the second one is about the solid solution of B in A plus particle form a new phase. Okay, actually for a larger amount of B. Okay, that means that we will form second phase particle. Okay, different composition and often different structure. Okay, it depends on the process. Okay, this one for the addition A4. Let's mean that mixture with uniform composition are called homogeneous mixture or solution. Okay, uniform. The keyword is a uniform. Mixture with the non-uniform we will call heterogeneous. Okay, the chemical in the mixture that present the largest amount is called the solvent. The other component are called solutes. Okay, and that's a term. Okay, the term you have to remember and understand very well, because after this one we will use the terms. Okay, this one is about the composition between A and B. Impurity is a B and host is a A in the system. Two description. Okay, the first one in terms of weight, percentage of the weight. The second one is a atom of weight. Okay, there's actually they have a normal formula you have to calculate. The first one is what the weight of percentage. Okay, the CB. Okay, for the CB is a impurity, a mass of the B, the total mass of the B divided by the total mass multiplied by 100. Okay, they will get the percentage same as a atom. Okay, then to conversion between weight and atom percentage in AB alloy. Cool. So you have to find the composition of the impurity B. Impurity is a B, so you have to use this formula. Okay. Okay. And then in terms of the atomic, you have to use this formula for the impurity. What is the percentage of the weight and also for the atom. Okay. So for the mass, okay, you just calculate within this formula. Okay, from this one we can convert it in the very brief it's not a value, very brief numbers, it's easier to understand. Okay, it's from the weight percentage, this one is for the atom percentage. Okay, there are several features of the solute and solvent atom are determine the degree to which the former dissolve in the latter. That's a very important, you have to remember. Okay, okay, because this the rule or law that you have to follow. That means the addition from the material B to the material A as a host. Okay, that we call it as a home rotary rule. Okay, this one we call as condition for such a solid solution. Okay, for solution we call SS. Okay, that we call the home rotary rule. The first one is a atomic radius or atomic size factors is mass less than 15% each other. And that means from the material A and material B to mixture, the size of the atomic size factor, the atomic size must less than 15%. That's a must. Okay, remember that. And the second one is about the electronegativity. Okay, that means they have to have similar electronegativity. Okay, if the negative, they have to negative. If the positive, they have to positive. The third one is about the crystal structure. Must same. It cannot be same. Must same. Okay, if the BC or FCC or FCP, they must same. Okay, between the material A and material B. Okay, the last one is about the valence or valency. Okay, must equal, being equal. A metal will have a greater tendency to dissolve a metal of higher valency than one or lower vacancy. Okay, they have a four rule you have to remember for the substance solid solution. This one is the same. Okay, this one is give you more detailed explanation. Okay, please refer this one. Okay, this one we have to remember. Okay, this one is a application of Home rotary rule. Is a solid solution. Okay, they give you an example. Okay, you can see here between the copper and nickel. You can see it's a copper, copper and nickel here. Can we see that the first one is about the atomic radius. Okay, mass less than 50%. Okay, we can see that the atomic radius for the cuprum is about 0.1278 nanometer. And then for the nickel is a 0.1246 nanometer. So we have to calculate mass less than 50% each other. Okay. The second one is about the crystal structure. Okay, mass same. The rule said mass same, mass FCC. So we can see here is a FCC, and also cupron is a FCC. Okay. The third one is a similar electronegativity. Okay. We can see here, we can see for the copper is 0.1 T and the nickel 1.8. It's okay if they have difference between number of one. Okay, but cannot until 5, 4, 5, 3, 4, 5 cannot. If the difference between only one is okay, no problem, we can accept it. Okay. The last one is a valence. Okay, for the valence is a 2 mass same. Okay, there's a rule you have to remember. Okay, this one the schematic representative of different point defects. So you have to remember, refresh back. Okay, refresh back. I don't want you to discuss, but without any refer to the previous slides, name it. What is a number 1? What is a number 2? What is number 3? What is number 4? And what is number 5? Okay, just name it. And refer back. And then refer back to the previous slide. Is it correct or not? If not, you have to study back. Okay. Alright, we go to the next subchapter about the line defect. We already cover only point defects. So what is the line defects? Okay. So line defects or discussion are type of crystalline defects that allow deformation or lattice distortion centered around a line. This one is a definition. What is definition line defect? And then you compare it with the point defects. So what is the definition of the point defects? What is the definition of point defects? Okay, point defect is a localized disruption in perfect atomic or ionic arrangement in a crystal structure. Okay, but the line defect, a type of crystalline defect, okay, that allow deformation or lattice distortion centered around a line. Okay, one is a distortion centered around a line, one distortion of atom. Okay, you have to compare with the line and point. Okay, dislocation are created during the solidification, during plastic deformation, consequent of thermal stress of crystal structure. This is the example defect of line. Okay, solidification during plastic deformation and consequent of thermal stress of crystalline solid. They are also formed by the permanent or plastic deformation by vacancy, condensation, by atomic mismatch in solid solution. Okay, that's another process that this question happen. Okay, this question are line defects. You have to remember that. Okay, and then slips between crystal plane result when dislocation move produce permanent plastic deformation. Okay, that's mean that you cannot go to the original back. Okay, the original one. Okay, in line defect, they divided into 3 categories. The first one is a edge dislocation. The second one is screw dislocation, and then the third one is a mixed dislocation. And then you compare with the point. The point is a vacancy, it's a shear link, and apa tu lagi? Okay. Apa tu lagi? Okay, boleh. Now vacancies, insertion and impurities. Okay, for the point tu insan defect, vacancies, sorry, vacancies, inter, detail, last one is a impurities. Okay, you have to compare. This one is a line. Okay, so why is location important? Again, we ask you why these locations are very important. The line, we know that we already discussed in terms of the point dislocation. Why is it important? And then how about the line? Why is it important? Okay, this one is a schematic of a zinc HCP. Okay, it's gonna close pack. Okay, remember that we already discussed in the last chapter. This one the original, the before deformation. Okay, this one we do the tensile. They have form slips, and then they will the elongates the material. Okay, and then to do the tensile one, the force is up and down. Okay, they have a slip plane. This one is the original materials. Okay, from SEM. This one is a scanning electron microscope. Okay, we can see that they have a slip plane. We call it a slip plane. Okay, the material is a zinc. Okay, we go to the first line defects is a edge dislocation. Is occurred in a crystal by the insertion of an extra half plane of atom. Okay, in figure 3.17a. Okay, this one. Okay, just above the location line symbol T. We call it a T. This one T. Okay, T terbalik tu. It's a T. Okay, displacement distance of the atom around the dislocation is called slip or Berger factor, and perpendicular to the edge dislocation line. This one. Okay, this one is a Berger vector. Okay, Berger vector. And then they are perpendicular with the edge dislocation. Okay, this one is a dislocation line. You have to remember. If they give you this diagram, you have to know this one is belong to edge dislocation. Okay, the keyword here is where is the Berger factor. Okay, this is a perpendicular or vertical, something like that. Okay, you have to remember, and then you have to find the dislocation line. Okay, so maybe they will ask, what is the Berger vector? It's not the Berger mill. It's not McDonald. It's a Berger vector. The magnitude and direction of the lattice distortion resulting from a dislocation in a crystal structure. Okay, that means they have a magnitude and they have a direction. That because a vector. There's a behavior of the vector. What is the vector? Must have magnitude and direction. So, what is tensile? Compression and shear test. What is tensile? Tensile. That means they have a force between two ways. Okay, and the compressor you press the material, and shear you have twist the material. Okay, that's a comparison between tensile, comparison, and shear. This diagram would like how to show you the edge dislocation happen. Okay, look at the A. Okay, it is a perfect crystal. Okay, and then for the B is cut and extra. For the perfect one, For this one, they cut in the middle. Okay? Cut in the middle. Or the half plane or half thumb is inserted. Okay, and then you inserted the other plane. Okay, you inserted the other plane half. Okay, not full, in the half. Okay, and burger vector is required to close slope equal atom spacing around the edge dislocation. So this one is a T. Okay, and then it's a burger vector. So this one is a look like for the edge dislocation. Okay, so how about the second one, about the screw dislocation? Okay, the first one is a edge dislocation. The second one is a screw dislocation. Okay, this type of line defect can be formed in a perfect crystal. Okay, by applying upward and downward shear stress. That's when you twist the material. Okay, you twist the material, or you applying force upward and downward shear stress to region of a perfect crystal that have been separated by a cutting plane. Okay, this shear stress produce a region of distorted crystal lattice is known as spiral ram of distorted atom or screw dislocation. See this one. Okay, you cut, for example, you cutting this one. Okay, and then you pull up, you twist. Okay, outward and downward apply the force. Okay. Okay. And this is a schematic for the screw dislocation. Okay. So this look like for the screw dislocation. Okay, example is a perfect crystal, and then you cut and share one atom spacing. Okay, and then the line of shear with shearing occur in this location. Okay, that's mean that you just outward. Okay, sorry, this one to apply force, and then you have a location. So you have to draw where is a burger vector. Okay. Okay, for the burger vector is a parallel. Okay, parallel. Okay, so the screw is a burger vector is a parallel. Okay, mana panggil parallel. Okay, parallel to the dislocation line. Okay. If the edge is a perpendicular. Okay, remember the differences between the screw and the edge dislocation. Okay, for the screw one is a parallel, for the edge is a perpendicular. So you have to compare it. Okay, so this one is a more example or more diagram to show you about the screw this location. Okay, to make sure that where it start and where is the burger vector. Okay, something like that. Okay, there's a example. Okay, the same actually. Alright, and then next is about the mixed dislocation. Okay, the mix up between the edge dislocation and screw dislocation. Okay, most dislocation crystal are mixed type. Confirm. Okay, combining edge and screw dislocation. Okay, in the curve dislocation line AB. Okay, from line A to the line KB. At the left, okay, a screw dislocation where it enter the crystal. This one. Okay, and the right is a edge location where leave the crystal. And this one will show you which one the screw location and which one the each location. You can compare about it. Okay, this one has a more schematic diagram to show you about the edge. Okay, screw and mix this location. Okay, one by one, and they are mixed up. Okay, this one is edge, this one is screw, this one is mix between. Mix is between. Okay, the between the mixture of the edge and screw. Okay, this one is a micrograph. Okay, macro diagram, because micrograph is a real one. It's belong to the iron. Okay, this multiplication is about 40,000 times, and the illustration appear is a dark line. Okay, this is a dark line. All the light dark is a this location. Okay, same as this one. This one belong to the titanium material. Okay, the dark line is a this location. Okay. All right. This one is about the dual location and crystal structures.